We're in section 1.5, and we need to talk about combining functions today. And I'm just going to go ahead and write these rules on the board, and then we'll work through some examples of it. But if you've got two functions, f and g, all right, two functions, f and g. These guys have overlapping domains. Overlapping domains. I'm just looking at how dark this black one is writing. This is probably not going to be good whenever I start trying to erase this. Let's see how it goes. Then you can say that the sum, and we'll write the sum as f plus g of x is equal to f of x plus g of x. So two different functions. We say f plus g of x. All we do then is just add the two functions together. And the process is going to be the same for basically all of these. We're doing a difference. In other words, subtracting one function from the other one. We have f minus g of x, and that would be equal to f of x minus g of x. We have a product, f g of x. We can rewrite that as f of x times g of x. And then finally, quotient, you're dividing So just note for this last one here, because we have division, we always have to make sure we don't divide by 0, right? So g of x cannot equal 0 in that case. But let's do a couple of quick examples. I'm not going to, they've got examples for like all of these in the book, but we're not going to do them all for time's sake. But let's say we've got f of x, 2x plus 1, and g of x equals x squared minus 2x minus 1. And they want us to find f of minus g of x, and then evaluate when x equals 2. And so this of the 4 over here, this is the difference one, right? We're doing a difference problem, and so that means that f minus g of x is simply whatever f of x is, which in this case is 2x plus 1, minus whatever g of x is, right? So we're going to put parentheses there so we make sure we don't mess the signs up. It's as simple as that, and then simplify. Yes?
Why is the difference problem again?
Say that again?
Why is the difference problem again? Why are we doing f minus g?
They just told us to. Right? It's a difference problem because we're taking the difference between f and g.
Oh, okay.
All right. And since that's what they asked for, then that's how we're going to plug that in.
All right.
Okay. All right. So let's just simplify. This is 2x plus 1 minus x squared minus 2 plus 2x plus 1. Right. We reverse the sign on everything that's in the parentheses there, and then we're just going to combine like terms, and we're going to put the the powers on the x in descending order. So negative x squared, 2x plus 2x is plus 4x, and then 1 plus 1 is going to be plus 2. Let's see. What did I do wrong?
Negative.
Oh, I did. This is supposed to be a plus. Sorry. That's supposed to be plus. So this should have been negative. My bad. I just copied that down wrong. So this, the 4x, it's not supposed to be 4x. The 2x minus 2x cancel one another out. And so it's x squared plus 2.
And then why did we reverse the signs?
Because we're doing f of x minus g of x. So because that's what this asks for here,
Yeah.
right? So I put minus, and then I put everything that was g of x in parentheses here so that we understand that this negative applies to the whole thing.
So the minus is the negative x squared. That's where the minus comes from.
That's, oh yeah, that's right here.
No, up one, middle one.
That's-
So that's the negative x squared, because you distribute it to the positive.
Yeah, exactly. Negative x squared, negative 2x,
All right. Yeah.
positive 1.
Yeah, I was trying to confuse
Gotcha.
why we reverse the signs and whether it's still minus.
Yeah. Gotcha. Does that make sense now? Okay. Cool. So that's the answer. If they just said find f minus g of x, we'd be done, right? But then they asked us to evaluate it when x equals 2. So then all we have to do is just say f minus g of 2, right, would equal negative 2 squared plus 2. We're just going to plug our 2 in there. And so that's going to equal negative 4 plus 2. And so our final answer is negative 2.
So we really didn't use it.
Any questions about that? So the process is exactly the same, right? Just depending on if it's plus, minus, multiplication, or division, right? We're just going to plug the whole function in and do this operation on it. So let's do, we'll do example 4, which is the quotient of two functions. And these erasers they just tend to sort of smear it. All right, so f of x equals square root of x. You guys, if I make a mistake when I'm writing it down, help me catch that, right? And g of x equals square root of 4 minus x squared. And so they want us to find f divided by g of x, and then find domain of f divided by g. Okay? So again, f divided by g of x, we're just going to plug in those functions, dividing one by the other. So f of x goes on the top, so that's square root of x. And g of x goes on the bottom, square root of 4 minus x squared. And so we're actually done. We just plugged it in. One thing to note on this is that 4 minus x squared is actually the difference of two squares. Do you guys agree with that? When you have the difference of two squares, you're able to factor that. Does that sound familiar at all? No? Okay. So you don't remember that x minus x squared minus 9. Have you guys learned that before? Maybe that's in this class. It's the same as x minus 3 squared. Oh, no, that's not true. That's not true. The difference of two squares is actually, yeah, this is what it should be. Right? You guys remember that? Okay. So when I first saw that, I was like, oh, it's the difference of two squares. We can get rid of the radical, but we can't because one's negative and one's positive. I was thinking about it. Okay, so it just stays like this. There's no way for us to simplify that further, right? And so we're done with that portion of the problem. I mean, I guess if you wanted to, right, you could say, well, since they're both under a square root, we could do it like this. I wouldn't count that wrong, but you don't have to, right? So what about the domain? When we're talking about the domain of f divided by g of x, what's the one thing that we need to be concerned about in this particular problem? Well, really, I guess there's two things, right? There's two potential issues with this problem. What are those problems, potential issues? Yes?
You can't have 0 or a negative number in the denominator.
You can't have 0 in the denominator, and we can't have a negative number under the radical. Is that what you were talking about with the negative number? Right? Saying it a different way. So that's okay. There's enough to get your name on the board. So nice job. So Stephen's right. We can't divide by 0. And anytime we're sort of, most of the time when you have these problems and they're trying to get you to figure out what the domain is, that's the trick, right? It's making sure you're not dividing by 0 and making sure you don't have a negative number under the radical. So for this particular one here, then in order for that bottom one to end up being 0, what can x not be? X cannot be 2, right? So we know that x cannot be 2. Because if x was 2, we'd have 4 minus 4 and the square root of 0, and so we'd have 0 on the bottom. So x can't be that. But then when we look at the other problem that we have is that we also know that 4 minus x squared has to be greater than or equal to 0. If we take this into account. So that means that 4 minus x squared minus 4 minus x squared has to be greater than or equal to minus 4. So we divide by the 1. So x squared has to be less than or equal to 4. And so we take the square root of that. And whoops, take the square root of that, sorry. Should have done that in the previous part. So x less than or equal to plus or minus 4. What? Yes.
Wouldn't it just be greater than 16 equals 0?
Yeah, it's true. That's true. Yeah, it can't be equal to 0 because we, because of what we found there. So thank you. I was gonna pull that out at the end and say we got to take this into account, right? This 2 can't be in there, but you're right. So x is less than plus or minus 4. Did I do that right?
I think it's 2.
Oh, I didn't take the square root. That's supposed to be 2. I'm just thinking about the plus or minus. They didn't really work that out. Yeah, 2, it can't be a number. So x has to be I'm sorry guys, I'm drawing a blank on what I'm doing wrong here as far as how you figure that out. Because what it turns out to be is that x has to lie between these values here. All right? So that's because if x becomes greater than 2, I'm thinking about this one up here, right? If x is greater than 2, then this ends up being a negative number, and we can't have a negative number on that, right? So x has to be in this range right here, but I can't remember how it is that you basically take that into account with your inequality. At some point, we divide this up into here. And when I was reading over this, it just didn't click with me, like actually working through the steps. I just glanced at it, it made sense to me that this has to be, x has to be within this range right here in order for it to make sure that it's greater than 0. Does that make sense to everybody? Right? So if we don't want this to be negative, then this has to be the range for x. But we can't actually set it equal to 2. It actually could be, based on what we have right here, it could be this. Right, it could be equal to -2. It just can't be equal to 2 because of this here. But this isn't the only piece that we have to take into account when we think about the domain. We also can't have a negative value there.
We gotta find the domain. Right?
So we have to find the domain in that one as well. So we can't have a negative number under this. So with the top part there, x has got to be greater than or equal to 0. Right? So let's write down all the domains together and let's see what overlaps. Okay, let's do it like that. So x has to be equal, x cannot be equal to 2. We have that on the bottom part. So we've got like this domain here. So we write that as -2 to 2. That's just for the bottom part. Does that make sense? You guys aren't responding to me at all, so I think I've lost you somewhere. Did I lose you, Stephen?
I don't know.
I should have never tried to do this with the inequality, so that was my mistake going down that path. We should have just looked at this and said, in addition to x not being able to be equal to 2, this also has to be true. And just write this like this. The way we would normally think about this part under the radical, which is g of x, the domain of g of x. If we just looked at it separate from f divided by g of x, we would say, well, 4 minus x squared has to be greater than or equal to 0. And so that means that x then has to be between the range -2 x, +2. So we would have this domain right here, which would be this guy. But because it's limited by this fact, since it's under the radical, then we would change that to be that, and we would change this to be that. And then for the other function, f equals the square root of x, we would say it's got to be greater than, x has to be greater than or equal to 0. So we would write that as 0, infinity. And so when it's all said and done with the possible values of x, this limits it to be between -2 and 2. But this says it's got to be 0 or greater. And so our final domain for this guy would be a combination of those, which would be, we can include 0, but we can only go up to 2 and not include 2. So because I sort of botched that whenever we started it, I'm going to take my time just going through this piece to make sure you guys got that. We're basically having to take the domain of everything into account, right? We really have 3 functions that we're thinking about the domain for. Thinking about the domain for this. What's the domain for square root of x? That function?
0 to infinity.
That's this guy here, right? That's the domain for f of x. What's the domain for square root of 4 minus x squared?
You can include.
I can include 2, right? So here it would be,
You can include negatives. We can't include.
if I just looked at this function alone, it would be that, right? But then when I bring it down, when I think about it being on the bottom of this fraction, now when I take f divided by g of x into account, then I realize it can't include 2, which is what we determined right here. And so then I take that away and I change it to that. So our final domain is going to be the intersection of these two here. And where those two intersect is from 0 to 2, with 0 included and 2 not included. So it's like the union of -2 to the union of that and 0 to. So when we combine those together so we can see what overlaps, we're left with 0. I wrote this wrong, sorry. 0 to infinity, my bad. 0 to infinity. So we're left with just 0. I wrote this wrong. Oh, I'm just messing you guys all up this morning. 0 to 2. That's where the two domains overlap. How confused are you at this point? Did the light bulb come on at all, Stephen, or is it still like, I don't see, man?
No.
You know how to find the domain of that, right? What's the only thing X? What's the only thing X can't? What do we have to worry about when we have a radical? We can't have a negative number under the radical.
Yeah.
So the domain of this is anything where X is not negative. So X has to be greater than or equal to 0. So this, right?
Yeah.
Yes.
For the domain of like the square root of 4 minus x squared, why can't it go below -2?
Why can't it go below -2?
Like, why can't it be -2?
But because let's say it's -3. So what's -3 squared?
9.
What's 4 minus 9?
Or would it be plus?
No, because it would be this. It would be 4 minus -3 squared. And so we're squaring this entire thing, which makes it positive. So now you get 4 minus 9. And so this becomes -5. And now we've got a negative number under our radical, which isn't allowed.
So how
So-
would -2?
So -2, if we were just looking at this, -2 would be okay, because it would look like this, and we would say 4 minus 4, and that equals 0. And we're totally okay with g of x being equal to 0. But we have a problem because in our final, in the combination of the two, g of x is on the bottom of the equation, and we can't divide by 0. So that's why we have to drop the -2 option here. Just because we can't have, actually, yeah, -2 or +2. Right? This was really wrong here. We should have said x can't be -2 or +2, because both of those would give us a 0 on the bottom. Yes.
So then why are you able to have a bracket on the left side of the thing?
Right here? Because it's just a 0, right? That's our final answer. The -2's out of the, we're not considering -2 anymore because we had to look at where both of these overlap, right? So if you think about that like a number line, so we've got two number lines here, and we've got a 0 point. Well, this number line here goes from, with what's allowed for this one, it goes from -2 to +2, right? And it's got a point there, and we got an open circle here. And our other one goes from 0, from this point here, all the way to infinity. So the only point where these guys overlap is this section right here, right? But we have to remember that it's an open circle on the 2, so that's why our final domain is 0, 2 within parentheses. Okay? Yeah, I messed you guys up by going down this path to start with. I should have just looked at it. And so I need to go back and refresh myself as to how you divide that up. How do I know? Because we ended up with something, like I said, that was x. Yeah, the inequality was messing me up. All right. It's just something that I haven't looked at in a while. I wasn't prepared to jump into it here, and they just kind of gloss over it. They just assume you can look at that and say what it would be, right? All right. Sorry for making that sort of confusion. The good news is this is really the bigger the bigger issue is making sure that you know what f divided by g of x is, right? And then remember our rules for domains, that you can't have a negative number under a radical, and you can't have division by 0. And so when you're doing these types of problems, you got to take all three functions into account, right? What's the domain of f of x? What's the domain of g of x? And then what's the domain of the combined function? And see where all of those guys overlap. All right. Okay, let's do a composition. And if you weren't confused enough, we're going to go to composition of functions. And this actually isn't that confusing, but we haven't seen this type of we haven't really seen this type of symbol used before when we talk about functions. And what this is, I always think of the word fog every time I saw this. I mean, from back whenever I was in high school, that's what I thought of. So that always comes to mind when you talk about the composition. But what this means is the composition, the way you would read it is it's the composition of the function f with the function g. And all that it means is that you're going to, so f, the composition of function f with g would just be take whatever g of x is and plug that into f of x. So you're taking the function g of x and you're plugging that in for every x value in f of x.
Say that one more time, the graph of g of x.
Say how, like how I explain the way that it works.
Yeah.
So you'll have two functions, you'll have f of x and you'll have g of x, right? And so if I'm finding the composition of function f with function g, I just take whatever g of x is equal to. Let's say g of x is equal to x squared. And I take that x squared and I plug it in for every value of x in the function f of x. So we'll do an example, and I think it'll click. It makes sense.
It's kind of the same thing. So like if g of x is one thing, it's really saying that f of x is that same.
If g of x is one thing, what?
So like if g of x is 2, then f of x is going to be 2, right?
F of x will be, well, they're two different functions, so we don't know what the two are. So let me do a quick example. I think it'll be clear if I do an example. Let's do this example, which is example 5. So they're wanting us to find the composition of f and g, where f of x equals the square root of x, and they note that x cannot equal 0. I'm sorry, x has to be greater than or equal to 0 because they're radical. And then g of x equals x minus 1, where x is greater than or equal to 1. So we've got some limitations on the domains of both of these functions. And then it says if it's possible, once we find what the composition of f of g, the composition of f with the function g, if it's possible, then find composition g of 2 and composition of g of 0. All right. Let's just find the composition function first. So all you do is you take whatever's g of x and you plug that into every value of x in f of x. Okay, so we just say the composition f of g is the square root of x minus 1. So all I did was I took what was g of x, which is x minus 1, and I plugged that into the x here. Make sense?
Yeah.
So let's just say, just for grins, let's say f of x is equal to square root of x squared minus x. If it was that, then we'd have to take wherever we had x in there, we would say is the square root of x minus 1 squared minus x minus 1. Right? Like that.
Okay.
Make sense?
And then, so with the composition and the square root of x minus 1, then when you had to solve for the composition of 2, you would just do, it would be 2 minus 1 is the.
That's right. You just plug in 2 for all those x values after you found this function. Make sense? Yes.
Why is it x minus 1 squared minus x minus 1?
This should have been, I wrote this wrong. Let me say this. I know that's right. I did that wrong. Right, my bad. This was, I gave you that as f of x, sorry. All right, so, and this is a separate problem, you understand that. That's not the problem I'm working. That was just an example. Just wanted to make sure you followed this. So if f of x was this, then f of g of x would be, you would take x minus 1, which is what g of x is, and you'd plug it in for every value of x. I'm just making sure you guys are understanding what we actually did. It's a little harder to see with this one because this function is so simple. Make sense? Okay. All right, so that's the answer to this question. What is f composition of g? But then they said, can we find f of g of 2? So if we did that, if we plugged in 2, and 2 is allowed, right, by both of these domains here. 2 is greater than 0 equals 0, and 2 is also greater than or equal to 1. So we can find f composition of g of x equals square root of 2 minus 1, which equals the square root of 1, which equals 1.
And then for f of g, and trying to find 0, can you still put 0?
You can't.
You can't.
We can't because of this limitation here, right? So that's right. So we would say for f of g, f composition of g of 0, we would say that's undefined. Here should be f composition of g of 2. Does that make sense? Just take one function and plug it into the other function. Whatever the second function is, the second letter here, right? You take that one and plug it into it. Let's do another example. And the example is f of x. This is example 8 in the book. F of x equals 5. What was that? Is that my phone?
Is it recording?
I don't know. It says it's still recording. Interesting. So f of g, they want us to find f composition of g of x. Right? So we're going to find that first, and then we're going to reverse it, and we're going to find g composition of f of x. So let's do this one first. So this is equal to 2. I'm just taking the f of x function, and I'm plugging in the g of x function. So 2, so x becomes 1/2 x minus 3 plus 3.
And you put that in because the composition, you're putting what g equals for x right there, right?
That's right. I'm taking this here, and I'm plugging in every
x.
x in this one. Yep. Everybody tracking with me so far? No? All right. So now, because we have 2 times the half here, and then that half is multiplied by this whole thing, and these guys just cancel one another out. And so we just have x minus 3 plus 3. So the final answer is x. Let's do B now. For B, they wanted us to find G composition of F. We're reversing things. So we'll take this function f of x and we're going to plug that into g of x. So that would be 1/2. F of x is 2x plus 3, right? That's our x value minus 3.
Do you need the second set of parentheses? Or can you just do?
I don't, but I always like to do that. One, so that it's clear to you guys, I just took whatever was here and slapped it into this x there. Because this is at the beginning, if my x had been here, if this had been reversed and it'd be 3 minus x, I absolutely would have used the parentheses just so that I didn't forget to run my negative all the way through this value here. But I like to do the parentheses just so it's clear when I'm showing it to you guys, and also it just helps me check the signs and make sure I'm not missing something, right? So now I can simplify it, and it becomes, I'm just going to combine like terms in here. So this is really 2x plus 3 minus 3. So the 3's go away, they cancel one another out. So I've just got 1/2 times 2x, and I'm left with just x. And so they could have asked us, the cool thing with this one is that f composition of g ended up equaling g composition of f. And so they could have just said, does f composition of g equal g composition of f? And then you had to do all this stuff to prove that it did.
They won't always equal.
They won't always equal, no. We're going to learn about a function in just a minute, but they will always equal. Okay, so let's go ahead and talk about that unless you guys have any questions. Let's talk about inverse functions. Any questions about composition functions? All right, basically, the way inverse functions work, what will be the case for inverse functions is that if I have one function f, and it's a set of points where 0, 1, 2, 3, -2, 4, -3, 1, whatever, right? A set of points like that. If f is the inverse of g, then what that means is that g will contain all of the points that f did with the x and the y's inverse. All right. So the set of points that define g would be 1, 0. I just flip those around. 3, 2, 4, -2, and 1, -3. So f and g are inverse functions if that's the case. So basically, the domain of one function becomes the range of the other, and vice versa. Because when we're thinking about domain, what values are we thinking about for a function? The x or the y values. If we're talking about domain, are we thinking about the possible values for x or the possible values for y?
For x.
For x. The domain is the possible values for x. So don't ever lose that concept, right? That'll be sort of a place for you to always come back to, and if you get confused on a problem, okay, domain is the possible x values, right? If I'm talking about range, I'm talking about the possible y values. Make sense?
So basically, the inverse function is just the exact opposite of the other function. So like you're just switching the values around, right?
Yep. Okay. And so what that means, and we're getting a little bit of ahead of ourselves, but what it means is that if two functions, if one is the inverse of the other, then they will always be symmetrical about this line here. And that line is y equals x. All right, so for every point over here, if it looked like this, then the inverse of it would look like this. And because that's what happens when you do what we did right here. You take every point and you take what was the x value and flip it, make it the y value, and take what was the y value and flip it, make it the x value. All right. So when you're thinking about, if I give you a function and I say find the inverse of the function, what you're trying to figure out is how to undo that function, and so that it will equal the identity function. The identity function is the line we just showed you, right? Y equals x, or you could say f of x equals x. That's the identity function. So, for example, example 1 of the book says that f of x equals 4 of x, and so how can I undo that? They want us to find f of -1 of x. That's how we write down the inverse function. F of -1 of x. And so what would f of -1 of x be? So that if I plugged in, this function, just like we learned about composition functions, for inverse functions, f of -1 of x should equal x. And likewise, f of -1 of f of x should equal x. So this is true for inverse functions. If I plug one into the other, I should always get the value of x. If I make one a composition of the other, I should always get the value of x. So think about that. If I'm looking at this function here, this top function, f of x, what value could I put in for x that would make this function just equal x? -4? If I plugged in -4, if I said f of -4, that would equal 4 times -4, and that would give me -16. So I need to be left with x, right? Anybody else want to take a stab at it? What can I plug in for x here that would give me, yes?
1/4.
1/4? Let's try 1/4. So if I plug in 1/4, 4 times 1/4 equals 1. We're getting closer, but we need to end up with x.
How do you mean what is that?
What's that? Say it again. What?
0.
0? Well, let's see if I plug in 0. If I go f of 0, that equals 4 times 0. That equals 0. I'm still not left with x. Think about it like this. You're going to have to plug something in that actually has x in it.
1/4 x.
1/4 x. That's it. That's it. All right. So, or we could say x over 4, right? So if we think about that, if I say f of x over 4, now if I plug that in right here, 4 x over 4, my 4's cancel out, and I'm left with x. All right, so that's what our inverse function would be. The inverse function would be x over 4. So let's try another one. What if I have f of x equals x minus 6? What would the inverse function of that have to be in order for the composition of one of the other to be x? What could I plug in for x to end up with x?
X plus 6.
X plus 6, exactly. If this is x plus 6, then if I do f of x plus 6, then that's x plus 6 minus 6 equals x. right? And the opposite of that would be true if I'm doing the f inverse. If I do f of -1 of x minus 6, I plug in f of x, then that would be x minus 6 plus 6 equals x. So if I do the composition back and forth of the two, I'll always end up with x if they're inverse functions. So that's the basic definition. If I give you a technical definition of an inverse function, it would be this fact right here. So let's just write that down so we have that definition. Definition of inverse function. It is let f and g be two functions such that f of g of x equals x for every x in the domain of g, and the reverse of that has to be true. G of f of x equals x for every x in the domain of f. I drop one more. Nope. Take the whole of that one. Just barely. For every x in the domain. Look at that. There's stuff here. So if this is true, then G is the inverse function of f. And G can be denoted by f of x. So like we said before, the domain of f must equal the range of f of 1, f -1, and vice versa. Now, like I said, if you graph inverse functions, they're going to be symmetrical around this line here, right? Y equals x or f of x equals x, however you want to think about that. So they'll be symmetrical around that. So just to kind of test that out, try punching these graphs here in your calculator. Do for example, we said for this one here that f of x equals x plus 6, and then we said that f inverse of x equals x minus 6. So if you plot those two, are they symmetrical about that line? Did it work?
Yeah.
Yep.
Are
Cool.
inverse functions always parallel
If they're lines,
to the one?
they're lines, right? But if there's something like the one in the book, you see,
So like a quadratic function or like a square root function, they would be parallel, right?
they're not, yeah, because parallels are only a concept that we think of as lines.
Okay, so but they would be still be symmetrical, right?
Yeah, it's always going to, like I said, if you have something like this, then the reverse is going to look like this, symmetrical about that. Okay? And remember what I mean by symmetrical, it means we could kind of flip it around that line there, this line here, and they would look the same. Right? And the reason that works is because of this. The domain of one is the range of the other, and vice versa. Now, to have an inverse function, you've got to have what we call a one-to-one function. So one-to-one function says a function f is one-to-one when for A and B in its domain, f of A, f of A equals f of B implies that A equals B. So that's what one-to-one means. And to sort of piggyback off of that, existence of an inverse function. A function f has an inverse function f of -1. IFF, if and only if, right? That's the shorthand way to write that. If and only if f is 1-to-1. What's that?
That's a lot of F's.
Yeah, it is. So if it could maybe be a tongue twister, right? If I give you a function and say, does this function have an inverse function? Then if you can, then if that will only be true if it's if you can prove that it's a one-to-one function. Okay. And what does that mean exactly? It means, when we were talking about functions, we said that write this down at the end. So here's function f, and here's function g. G is so one of these is actually a function and the other one is not. Which one is not a function? Top or the bottom? F or G? Which one? F. Why is that, Diego?
Because of the 1, 0 and the 1, 2.
That's right, because for it to be a function, you can't have any two x values be the same with different y values, right? But it's totally okay to have different x values that have the same y value. So this one here, we've got 3 for the y value and 3 of these points, but they all have different x values, so it's okay. This, however, is not okay if it's a one-to-one function. For every x value, there will be a unique y value, all right? And so that's really what this one-to-one definition is saying for you. So even though t is a function, it is not a one-to-one function, right?
This is basically saying that a one-to-one function is just a unique point.
That's right.
Point on the graph for every single domain, which you can't have.
Well, and these are unique points, but they just have different y, but they have the same y value.
So as a completely unique x and y value.
And so there's a quick test graphically to figure this out, and that's this. Is this a function?
Yes.
That is a function because we can do the vertical line test, and every vertical line we can draw will only go through one point, right? But what about horizontal lines? If I draw horizontal lines, they go through multiple points. The horizontal line test will tell us whether or not a function is a one-to-one function, right? If it crosses 2 points on the graph, then it is not a one-to-one function. This would be a one-to-one function, because no matter where I draw a horizontal line, it only crosses 1 point. So is not one-to-one, is. All right, so we call that the horizontal line test. All right. So that's the quick test. So what we ran out of time being able to do in section 1.6 is finding the inverse function algebraically. Sometimes, we did some really simple ones where it was easy to just look at it and see what it would be. Sometimes it's not that easy. So next time we'll talk about some steps for finding that out. All right, so we ran out of time just a little bit today, and we had one more concept we wanted to get to, which was being able to, we did some pretty simple equations where we were trying to find the inverse function of an existing function. But I said right at the end that some are going to be more complicated. So we needed some steps to go about finding the inverse function of another function. So these are the steps that are listed in the book for finding an inverse function. The first thing, of course, obviously you want to do, if you can view a graph of the function, just make sure it meets it passes the horizontal line rule test, right? Can you pass a horizontal line through the function that intersects more than 1 point? If you can, then there is no inverse exists for that function. All right, but if you can't, then we can proceed on to step number 2. So you're basically going to, instead of f of x for your function, write down, replace f of x with y. That's step number 2. Step number 3 is then exchange x and y. So wherever x was in the previous one, put y there, and y then becomes x. And so then you're going to rearrange that equation and solve for y. And then that basically becomes your inverse function. You replace y with f to the -1 of x. And then you have to verify that the domain of f is the range of f the -1, or the range of the inverse, and vice versa. The domain of the inverse function is the range of f, right? So, and the final test is, of course, to verify that if I do one as the composition of the other, I should get x, right? So let's do an example so that we can actually understand what that means. So the example they have in the book, this is example number 8, says f of x equals 5 minus 3x over 2. All right, so let's look at the steps that we have over here. We're going to assume that an inverse exists. We can plug that in our calculator, and we can check it. And they've actually done that for us. There's a little picture of the graph there that shows that indeed it passes the horizontal line test. And so we can proceed to step number 2. So we're going to replace f of x with y. So it looks like this: 5 minus 3x over 2. Then we're going to take all the x's and make them y's, and all the y's and make them x. So it will look like this: x equals 5 minus 3y over 2. And then we have to solve for y. So if we do that, we're going to multiply both sides by 2 and get 2x on this side equals 5 minus 3y. We'll bring the 5 over to the other side. So 2x minus 5 equals negative 3y. And so if we divide both sides by negative 3, we get y equals negative 2x. If we multiply through by this, we'll get negative 2x plus 5 over 3. And so they did 5 minus 2x over 3, but either's fine. So this would be the inverse function. Whoops, threw my 3 accidentally. That would be my inverse function there. And in order to verify that that indeed is the inverse function, then we do a quick look to make sure that the domain and the range of each match up. So the domain of this function should be the range of this function down here. And if we look at this, the domain of this is all reals. There's nothing there's no division by 0 that's possible. There's no negative values under an even root that would be possible. So we're good, all reals there. And as it turns out, this function would have that's the domain of this function. And the range of this function would be all reals as well. And we have the same thing down here, right? The range of this one, if the domain of the top one should be the range of the bottom one, and they are both all reals, and then vice versa. So the only other thing we need to do is we need to plug each one in the other and see what we get. So let's do that. They don't do this in the book, so I'm going out on a limb here, hoping that this will work out. But let's plug in let's take the bottom function. Oh, I did forget a step here, right? One of the things it said to do was we needed to take our y and we needed to replace it with f of negative 1 of x. All right, so that identifies it as the inverse function of f of x. There we go. All right, so let's do f of negative 1 of x. So let's plug that in there. And what do we get? We've got 5 minus 3. And for x here, we're going to plug in negative 2x plus 5 divided by 3. And all of that divided by 2. And so our 3's are going to cancel out in this equation. So on the top, we're left with 5 minus, no, not 3, 5 minus negative 2x plus 5. All of that divided by 2. That, just to give us enough room, we'll move over here. That's going to give us 5 plus 2x minus 5 divided by 2. And so sure enough, the 5's are going to go away. We're going to have 2x over 2, and 2x over 2 is x. So we get x for that. So now we'll go the other direction, f of negative 1 of f of x. Does that also equal x? And so let's try that. So we've got negative 2. For x here, we've got 5 minus 3x over 2 plus 5, all of that plus 5 divided by 3. And so on the top, the 2's are going to cancel out. And so we've got negative 2 times a positive 5 is going to be negative 10. Negative 2 times a negative 3x is going to be a positive 6x plus 5, all of that divided by 3. And this is not, let me double check and make sure that we're getting, because we've got 5x on, this is not simplifying the way that I expected it to. 5 minus 3x. What did I do wrong, guys? Negative 2x plus 5. So negative 2, 5 minus 3x over 2. All of that plus 5 divided by 3. 2's cancel out. Oh, that's where I messed up. All right. So sorry. Maybe I'll edit that out in the final video. We'll see. So yes, these 2's canceled out. I forgot to cancel my 2's out, right? So on the top, I've got negative 5 plus 3x plus 5. Now there we go. The 5's go away, and we've got 3x over 3, which is in fact x. So both of them check out. We did, in fact, find the inverse function of that problem. So let's do one more just to make sure that you're tracking with me. Let's erase this stuff. I want to leave our steps up there, so it's going to take me a minute to erase this. All right, so the other problem in the book is on page 66, and it says, it's example 9, and it says f of x equals x cubed minus 4. F of x equals x cubed, oops, sorry, f of x equals x cubed minus 4. All right, so we're gonna follow our steps again. We have the graph picture on there. We can punch x cubed minus 4 in our calculator, and sure enough, it passes the horizontal line test, so we can continue to move forward to step number 2. So put y in the place of f of x. So y equals x cubed minus 4. Now exchange the variables. So we got x equals y cubed minus 4. And we solve for y. So x plus 4 equals y cubed. And so we're going to take the cube root to get rid of that, the cube on the y. So that means that the cube root of x plus 4, all that equals y. All right, so we replace that with f negative 1 of x. And so we're saying that this is our inverse function, right? So let's plug that guy. Let's plug them in one another. Again, just doing a quick look. What's the domain of this one up top? It is going to be all reals, no limitations. Here, because we've got a cube root, it doesn't matter if we have a negative sign underneath it, right? So it's going to be all reals as well. And so the range will be all reals for both, and the domain is all reals for both. So we're fine there. So let's plug one in the other. So f of negative 1 of x is equal to the cube root of x plus 4, all of that cubed minus 4. And so if we do that, the cube, cubing the cube root just takes that away. So we've got x plus 4 minus 4, and sure enough, that equals x. So let's do the same the other direction. F negative 1 of f of x equals the cube root of x cubed minus 4 plus 4, right? We took f of x up top here, which is x cubed minus 4, and we plugged that in our equation at the bottom here. And so that gives us the cube root of, the 4's go away, the cube root of x cubed, and sure enough, that equals x as well. So we've proven that the cube root of x plus 4 is the inverse function of x cubed minus 4. All right, so that's it. That should get us through the rest of the problems, and we should be able to move on to, should be able to complete all the homework in that section. So please reach out if you have any questions, and Lord willing, I will see you guys on Monday.